Welcome back to another AP Stat video. We're going to start off by doing some examples of binomial distributions and then introduce geometric distributions. So first of all, to review the calculator steps for binomial distributions, you can use binomial PDF, NPK, when it is the probability that x equals k for n trials and p probability of success. You can use binomial CDF, NPK, when the probability is less than or equal to k. So if it's not less than or equal to k, then you'd have to change it to be a less than or equal to k. So for example, if it's less than k, this is a discrete distribution, so that's going to be the same probability as less than or equal to k minus 1. It's easier with numbers, so I'm going to do that with numbers. Let's say it was the probability that x is less than 7. That's the same thing for binomial as calculating x is less than or equal to 6. If it's x is greater than 7, then you can do the opposite probability, so 1 minus the probability that it's less than or equal to 7. And if it's x greater than or equal to 7, that's the same as the opposite of probability that x is less than or equal to 6. So remember, you can always rearrange your inequality to be able to use binomial CDF. That will be a lot quicker than typing in 1 and then 2 and then 3 and then 4, finding all the individual probabilities and adding them. So let's take a look at this example. Seed Depot advertises its new flower seeds to have an 85% chance of growing. So that's our probability of success, 0.85. Suppose that the company's claim is true. So Judy buys 20 seeds and plants them in her garden, and the X is the number of seeds that germinate. So she wants to figure out that if she plants all 20 seeds, what's the probability that 17 of them germinate? And so that's going to be binomial PDF. With 20 trials, probability is 0.85, and we want to know 17. And so you'll go to second bars in your calculator and go down to binomial PDF, type this in, and you get 0.2428. Part B is asking if only 12 seeds germinate, should she be suspicious that the company's claim is true? And so we're going to try to figure out what's the probability that 12 or fewer germinate and see if that's a very low probability of happening, because 85% would be like, what would that be? 18 seeds germinating, that'd be 85%. So we're going to see if it's unusual if 12 or fewer germinate. So we're trying to see the probability that less than or equal to 12 germinate. So that's binomial CDF now, 20.85, 12. And when you type that into your calculator, you get 0.0059. So there's less than a 1% chance of less than or equal to 12 seeds germinating. So should she be suspicious that the claim is not true? Well, if you think about it, we would expect 85% to germinate. So the company's claim could still be true, and that would be unusual for this to happen. So it's unusual for this to happen. So the claim is probably true. Alright, so just like any distribution we've done so far this year, you can calculate a mean and a standard deviation for a binomial distribution. And this is helpful if you want to do like a normal approximation instead of using binomial PDF and CDF. And these formulas are provided for you on the formula sheet. So the mean of a binomial distribution is n times p, and the standard deviation of a binomial distribution is the square root of n times p times 1 minus p, so where n is the number of trials and p is the probability of success. Alright, so we've been doing a roulette example so far this unit, and the probability of landing on black was 18 out of 38, if you remember from previous videos. So we're going to calculate and interpret the mean and standard deviation for this scenario. So the mean of x is going to be 10 spins times 18 over 38, which when you type in the calculator is 4.74. So in 10 spins, you can expect to land on black about 4.74 times. That's the mean of this binomial distribution. And the standard deviation is square root of 10 times 18 out of 38 times 20 out of 38, and that equals 1.579. So we're going to interpret this in 10 spins. The number of times you land on black typically varies from expected by about 1.579 spins. And so we can use the mean and standard deviation to estimate without having to use the binomial distribution. And so how often will the number of spins land on black be within one standard deviation? So they're asking plus or minus one standard deviation. So that's going to be 4.74 plus or minus 1.579. So somewhere between 3.161 and 6.319, we would expect to land on black somewhere between 3 and 6 spins. And so what percent is that? The percent of the time is between 3 and 6 spins. If I subtract that and divide by 10, that's going to give me the average, because there's a range of 3.158 spins. Divide that by 10, and that gives me the percent of the time that I'm landing on black, 3158. So about 32% of the time you will land on black. That's our estimation within one standard deviation of the mean. So this is called a normal approximation. We know from previous chapters that within one standard deviation on a normal curve, it's 68%. So obviously this is just an estimation and not usually accurate. So let's take a look at a couple other examples. Go ahead and read and try this NASCAR example. Hit pause and try it, and then hit play so you can see the answer. So here's the answer to this NASCAR example. And you'll notice that I showed you the binomial PDF way of doing it or the by hand way of doing it using 6 choose 2. Now normally I would do this because sometimes on multiple choice questions they leave it worked out as the 6 choose 2 and they don't actually give you a probability. But as you know that for the AP exam this year you don't have to worry about that. So I think our test is going to just be free response for this unit so we can start getting used to no multiple choice. So that's a review of binomial distributions. Now we're going to move on to the last type of distribution, a geometric distribution. So a geometric distribution is where you repeat the chance behavior until a success. So the difference is in binomial, you had a set number of trials and you were counting how many times you had a success. With the geometric setting, you're going to keep flipping your coin or you're going to keep rolling your die or whatever chance process you're doing. You're going to keep repeating this chance process until you have a success. Once you have a success, you stop. And so the conditions are it needs to be independent trials. So flipping a coin, for example, every coin flip is independent. And the probability of success has to stay the same. All right, so a geometric random variable, you know for binomial we've been using x as the random variable. So for geometric we typically use y. So y equals the number of trials it takes to get a success. So these are also discrete with y starting at 1, 2, 3, and so on. And the parameter of interest is you have n is going to be the number of trials until success, and p is the probability of success. Let's look at an example of a geometric distribution. So this is a Monopoly example. In the board game, one way to get out of jail is to roll doubles. Suppose that the player has to stay in jail until he or she rolls doubles. The probability of rolling doubles is 1/6. So why is this a geometric setting? Well, first of all, every dice roll is independent. So we have independent trials. The same probability of success every time. There's a 1/6 chance of getting doubles every time. And the last one, and the one that separates it from binomial, is that you are rolling until you get doubles. That's what makes it different from binomial. Binomial would be like, if I roll this dice 10 times, how many will land on doubles? This one is, I'm going to roll these dice until I get doubles. So we've got y is the number of rolls it will take to get doubles. And then the probability of y is the probability it takes each amount of time. So like the probability it'll take 1, the probability it'll take 2, and so on. So this geometric has an exponential looking distribution. If you remember when you did geometric sequences in your algebra classes, a geometric distribution looks exponential. So the distribution of a geometric variable looks exponential. So you don't really need to know that, but that's just a fun piece of information there. So we're going to find the probability that it takes exactly 3 rolls to get out of jail. So we're going to calculate, that means we're going to fail twice and then have a success, right? We're going to roll twice and not get doubles, and then we'll get doubles on the 3rd try. And so there's a 5/6 chance we fail, 5/6 chance we fail, and then 1/6 chance we succeed. So we'll multiply all those together, and you get 0.116. And so really the way that you should do this is by setting up some exponents. The probability that y equals k is going to be the probability of failing to the k minus 1 power times the probability you succeed. That's always what it's going to be. So exactly 4 rolls, the probability that it takes 4 rolls will be I fail 3 times and then I succeed. And so that's going to be 0.096. What about 100 rolls? What's the probability it'll take 100 rolls to land on doubles, which we know is very unlikely. You're bound to get doubles before then. That means I would fail 99 times and then succeed. And that's going to come out so small, I'm not even going to type it in the calculator. So in general, we have this formula that is on the formula sheet. The probability that y equals k is the probability you fail to the k minus 1 times the probability you succeed. And the mean of a geometric distribution is also on the formula sheet, but it's 1 over p. So for the monopoly example, you would do the mean of y is 1 over 1/6, which is 6. So you can expect it will take 6 rolls to get doubles. And so here's the general formula for the mean of a geometric distribution. So we'll do one more example. What is the probability it takes longer than average to escape jail? So they want to know what's the probability it will take longer than 6 rolls to get out of jail. Well, there's the long way, and that's where you could do the probability of 1 plus 2 plus 3 plus 4 plus 5 plus 6, and then 1 minus that, right? Or we could use geometric CDF. And it goes the same way as binomial, but you have just P and K in your parentheses. And you still have to follow the same rules. It's got to be y less than or equal to k. So right now we have y is greater than 6. So we're going to do 1 minus the probability that it's less than or equal to 6. So that's going to be 1 minus geometric CDF with the probability of success being 1/6 and 6 rolls. And so that's going to be 1 minus 0.665, which is 0.335. So the probability that it will take longer than average to land on doubles is 0.335. And so again, it looks like it's an exponential distribution, and it's skewed right. So it kind of looks like this. It's exponential decay, which if you look at the function, you know that the probability that y equals k is 1 minus p to the k minus 1 times p, right? Well, 1 minus p is going to be less than 1, which we know is going to be exponential decay. And so a geometric distribution looks like an exponential decay function. And that is why if I put 6 here, you've got a smaller area under the curve on the right side of the average than you do on the left side of the average. So the distribution is skewed right. And we could have said that just by looking at the probabilities, there's less than half of the data to the right of the mean. And so that is the end of Chapter 6. Make sure you work on some Chapter 6 homework questions so that you're prepared for your test. We're going to take a quiz on Friday over 6.3, and then we're going to review next Tuesday and take a test next Thursday. I will open up the test early, so if you want to get it done earlier in the week before your spring break, you can. See you next time.